All right, and we're just going to take a look at some of the problems in this packet and marvel at my ability to craft gifts here. So this comes from a great classic 90s music video by the Beastie Boys, song Sabotage. Album is Ill Communication. Check it out on the Spotify later. They're fantastic. And I think it might have been Check Your Head was the cassette tape that my driver's ed teacher tossed out the window because we weren't allowed to have swears on the music we listened to while we were driving. We could bring our own tapes, but if there were swears, throw it out the window. So, somewhere in a guttering country. Still my copy of Check Your Head. See the car going over the hill here, and this differs a little bit from the problem that we're going to do, but it kind of gives you a little bit of a clue as to what's going on in the free body diagram. Okay, so that's what I'd like you to be thinking about here. As this car goes over the hill at a constant speed, on the whiteboard you can be thinking about the motion map and the answer to question B. Sorry, this is not the one I want to look at. I want to look at, yeah, this is the one I want to look at. Never mind. The car's going 43 kilometers per hour. Its mass is 1,200 kilograms. Radius of the hill is 25 meters. And you're to determine the magnitude of the force the car feels from the road. So that's what I'm looking for you to put in to the pair deck. And it's not MKQUI. It is Puel. Spell that right? Yep. All right. So go ahead and get after that with your classmates. Koba.
So remember, like, acceleration is pretty stands for over R.
Just, yeah.
It's all sure to what's the measure again? Remember those two?
Oh, yeah.
This is just like the really important thing. So we have velocity, we have radius, we have mass. Yeah. So for figuring out acceleration, you have velocity and radius. What's that? Acceleration is 9.7 squared, and that's towards the sun. So magnitude of force from the road. Right. Okay. Well, what's that?
Bro.
So it's just going straight. So it's accelerating in what direction? Acceleration. Yes. I mean, think about that. It's gravity becomes bigger. Magnitude of force that car Oh, so this is acceleration towards the center, but we also have acceleration to the gravity. So we know that it's feeling down when you do something gravity. But net acceleration down is 5.7. So that minus that should give us this nutrition action on the road. Instead it gives us what we need acceleration. So times its mass gives us the force and radius. So because I'm going to be expecting gravitational acceleration on this.
Sorry.
10 newtons.
I'm just looking for you to drop the number value, the magnitude of the force car feels from the road. Throw that into the pear deck. It's just a number right now. I don't need.
So we're trying to find the force, right?
Yeah.
We have acceleration, we have mass. Mass and acceleration is force. So acceleration force it's in kilograms.
Yeah.
The 2, 4,120 newtons roughly. Construct a quantitative force at the moment of time. Force is balanced while accelerating, so it should be enormous. At the top of the hill, we've got gravity going down. And we know that there is a net unbalanced force. It's accelerating down to 7, so the force is smaller.
All right, I've only got answers from a few of you in here right now, so let's have a few more join us.
Yeah, so that's what
Number value for what you get for that magnitude of the force the car feels from the road.
mass. Subtract from that.
Yeah.
Couple of things to have on your radar. There's some reading assignments over here if you didn't do those yet. During your copious amount of time away from school. Also, this mastering is due tomorrow night, so hopefully you've gotten a chance to get started on it. It's kind of plug and chuggy, especially in light of the stuff we're working on here. So hopefully you can get after it during AFT, and if you got questions, I'm in here too. But of the 10 problems on there, I think almost all of them are coming in as ones right now, meaning they're hopefully not too awful. All right, now we've got a few more answers in here. So some folks are coming in right around 5,000. Some folks are coming in right around 7,000. Some folks are coming in somewhere around 88,000. So ponder those for a second. Just kind of double check with your neighbor and make sure that you're giving us the answer to the question that we're asking. The question that we're asking is magnitude of the force the car feels from the road. Okay, so keep in mind if the car is at rest here, then you'd have balanced forces. You'd have FG down, and that would be about 12,000 newtons. You'd have smoosh push up, and that would have to also be 12,000 newtons. As far as like problem solving strategies, when you're looking at these problems, try to be mindful of how is this a circle? Okay, and in this case with this hill, it's a really badly drawn circle that looks like that. Okay, here's the center, and it's got a radius of curvature of 25 meters. But if that's the circle, there needs to be an unbalanced force pointing towards the center of that. Okay? And to the free body diagram, then that means we need to have an unbalanced force pointing down. So I'm still going to have this 12,000 newtons of FG because nothing's changed there. But then if we get at the equation here, be mindful. It looks like a lot of you had picked up on this, that the equation solving for the unbalanced force. So 1,200 kilograms, 43 kilometers per hour. But if this is going to all be in newtons, then you're going to have to sort that speed out into meters per second. That's about 11.9. So we're going to square that and then divide by the radius of 25 meters. So you get somewhere in the ballpark of 6,848 meters. Sorry, I'm getting distracted here. 6,848 newtons. That's the FU. So in my diagram, that's going to have to begin at the beginning. So it's going to touch its butt to this arrow's butt. This is 6,848 newtons. We got to figure out the smoosh push then. Okay? So FG less the smoosh push is equal to that 6,848 or thereabouts. And so that's where we're getting the smoosh push in the ballpark of 5,152 newtons. That's the force the car feels from the road. Okay, so in that situation, the smoosh push is less than the gravitational force. And that's why you feel a little bit lighter when you're going over the top of a hill. It's kind of like when the elevator is accelerating downward. This time the centripetal acceleration is downward. You're going to feel a little bit lighter. Okay. If we take that back to the video, though, in the video, and I can't pause a GIF, I don't believe, but if you're watching this, you see a little bit of daylight under the tires as it goes over the top of the road. So let me adjust my my diagram slightly here. Okay? So if there's a little bit of daylight underneath there, it's not touching the road. Think about what that says about the free body diagram. And what is that velocity to lose contact with the hill? Go ahead and sort that out with your neighbors. And I'll hit you up over on the Pear Deck for that number. Again, once you've got your number value for what is that magical speed whereby the car loses contact with the road, go ahead and dump that into the Pear Deck.
So you added gravity. Is that what you're saying?
All right, so we're getting answers in the neighborhood of 1643 or 142. Again, if it's leaving contact with the road, you're not going to have any smoosh poosh. You're just going to have gravity. And if that's the only force that's acting on it, then your unbalanced force is going to equal your gravitational force. Okay, Fuch and Fg are going to have to equal each other. So this is m v tan squared over r. And again, how do we calculate Fg? You take the mass times g. You take the mass times 10 newtons per kilogram. So if you look at that, clearly the mass is going to cancel on both sides. V tan squared equals GR. So V tan, that's going to be the square root of 10 times 25, square root of 250. 15 is the square root of 20 or 225, so we're in that ballpark. (15-ish) meters per second. Okay, so a little bit faster than it's going right now, and it'll leave contact with the road. You would have a similar free body diagram inside the car. You would not experience a smoosh poosh from the seat. Okay, you would feel weightless. You don't have to go into outer space to get that weightless sensation. You crest this hill at 15 plus meters per second, and that's where you're going to be. All right. So then let's pivot over to the opposite end of this problem. You've got the car going through the trough. So if you look at the video here, you see how the springs compress. So think about what that means dynamically in this situation. If the spring's getting compressed, what's happening with the interaction with the road? Again, you could be thinking about the motion map and the acceleration and its direction. But my suggestion, visualize a circle here. If it's going in a circle, the Fuchs got to point towards the center. And think about how the free body diagram's got to lay out. What I'm looking for you on the pear deck is you just will not let me. There we go. All right. On the pear deck, what is the magnitude of the unbalanced central force the car experiences? Okay, so go ahead and have at that with your neighbors. Waiting for responses for a few more of you here. Again, it's asking you to determine the magnitude of the unbalanced central force that the car is experiencing here. All right, we're looking pretty good here. A whole lot of 30,000s, got one 18,000 there. What do we need to let our friend know? It's 1 newtons, but what are you doing if you're getting 18,000? And is that going to be the force of the road here? So in this situation, we just slap in the math, and the unbalanced central force, that's going to be 1,200 kilograms. This is 25 meters per second. That's going to get squared. That's over 25 meters. So yeah, that's going to shake out to a Fuch of 30,000 newtons. But if you think about this free body diagram, so here's our circle, and the center of it is here. So this one's going to be Fuched up. To make that happen, if you've got 12,000 newtons of Fg, okay, we want to have, let me move this down a little bit. We want in the end to have 30,000 newtons of Fu pointing up like that. And again, when we're talking about unbalanced force, that's going to be tail to tail. So this smoosh poosh has got to be the combination of those two things. It's not asking for the smoosh poosh here, it's asking for the Fuch. But if you're actually solving for the force the car feels from the road here, that's going to be 42,000 newtons. Okay. So again, be cautious about how the forces lay out in the diagram. This one did ask for the Fuch. Problem 3 on here, I've got a pretty detailed solution already up on Canvas. And then I think we'll come back over to this and deal with 4 a little later. But I wanted to refer to one other thing that I had on the Canvas from that day. And that's this thing.
Good, right? Good camera? Yeah, good. My name's Dane Walters, and I'm a stuntman who does tumbling, gymnastics, and parkour. I'm attempting to run the loop, because I've seen people do it on skateboard before, I've seen people do it on BMX before, but no one's ever tried it on their feet, so it'd be nice to be the first guy to actually run it. It looks a lot bigger than what I thought it was going to be. Yeah, I must admit, not the easiest thing I've ever done.
So if you look at them while they're constructing this loop-de-loop, come on, you can kind of see how there we go, how the center of it is about feet high, okay? So just to roughly ballpark the radius of this thing at about 2 meters, okay? Sort of standard human height, maybe a little bigger than that.
One of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
Basically boils down to this centripetal force. You need to keep on accelerating. So you need to reach a certain speed. Mm-hmm. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour.
That it?
That's it.
Okay. 3, 2, 1, go. 17. 85 minutes. Can somebody share that one back? Oh, this one.
So the problem he's running into is if he's not fast enough, it kind of falls away from the surface right at the top. I want you to first think about, okay, if he is going fast enough, he maintains contact all the way around here, what is his free body diagram going to look like? Can you kind of run that on the pear deck there real quick? So you're putting him, he's at this point in the loop-de-loop. What is his name? Damian Walters? What do I want to do here? All right, so kind of compare and contrast these two ideas here. Does one of those look a little bit more like what you already have on your diagram, or is there one you can see your way to agreeing with a little bit more than the other? All right, so are you an A or a B here? Add a little bit of the Y in there as well, if you could. All right, let's see what our friends are saying over here. B, unbalanced force should be pointing to the center of the circle. B, accelerate towards the center of the loopy thing in contact with the loopy thing and still feeling force from the gravity. A, there's no upward smoosh poosh. A, because the surface of the loop pushes him down. A, why is the smoosh poosh in B pointing upward? A, because the FU must point towards the middle and the smoosh poosh that he's experiencing is also pointing down. So, yeah, be mindful of that. If you look at it in the image, he's under the road, right? The road or the track is above him. If we draw smoosh poosh pointing away from the surface of the dealer. So you're going to have gravity pointing down, but it'd be like if I was pushing against the ceiling in here. So the smoosh poosh is pointing down. Now, what they both did agree on is there should be unbalanced force towards the center, but be cautious about the direction of the smoosh poosh there. Okay. If we watch on here a little bit.
One's it. I know I've said that 3 times now, but this one is it. Well, I'm close. I reckon I'm close. Getting close. You can't really go any further until you take the match out. Yeah, let's get rid of it. Anyway, go for it.
Okay. So if you imagine if he's doing this at the slowest speed possible, then the smoosh poosh should be even smaller than that. Maybe it would just be a little bitty micro smoosh poosh there. Okay. What would be the speed? What's the kind of the minimum velocity necessary for him to maintain contact at the top of that loop of 2 meter radius? Okay, go ahead and check that out with your friends and neighbors real quick. So again, it doesn't matter how massive he is. That's going to cancel out here. We've got kind of the same setup again. Because the Fook is going to be equal to the gravitational force. So square root 10 times 2. And it looks like most folks are in reasonable agreement there. It's somewhere in the ballpark of 4.4 meters per second for the minimum speed. He's got to go faster than that. Now, if you want to kind of get a mental sense of what that is, if you take the meters per second and multiply it by 2.25, that'll tell you the miles per hour, somewhere in the ballpark of 9-ish miles per hour. And I didn't have the audio up earlier, but if you catch this part of the video,
basically boils down to this centripetal force.
So-
you need to keep on accelerating. So you need to reach a certain speed. And I've worked out, it's quite good news actually. The speed at the top is 8.65 miles per hour. That's it.
Okay.
so it's kind of like in class, the girls doing all the work on the whiteboard and the boys are just kind of standing around drinking sodas. But she said 8.6 miles per hour. That's what she had for the speed there. So pretty good agreement with the 4.4 meters per second that most of you have there. 2 meters is probably not a bad estimate for the radius of that thing. All right. So those are kind of some good initial examples of how to deal with some of these circle problems. The problem with the bank turn, okay, we'll address that tomorrow, but let me show you. Ooh, that's not great. I don't know if I can get there from here. Network? I can't show you anyways. Ooh, maybe I can. I'm a teacher. How did I lose my bookmark? So have a little think about the free body diagram here. What is contributing to the unbalanced force pointing towards the center of the turn? Have a good one.